Now we know the substitution theorem's not going to work for us. So we're just going to use some algebra, distribute things through, clean it up, see what cancels, and pray with everything we've got that we can factor in h out of the numerator of that fraction. So let's do that. Notice also that any time an h shows up, I'm writing that limit notation, just like we learned using the main limit theorem. When we evaluate limits, we do not drop that limit notation until we are actually evaluating the limit. So let's expand that. That will be x squared plus, we're going to have 2hx's. Hopefully you can see that. I'll come out over here, x plus h times x plus h. First is x squared. Outside is x times h. Inside is x times h. It is my habit to write any term that has more than one variable in alphabetical order. And that is my habit so that later on down the line, down here someplace, if that variable shows up again, I will for sure write it in the same order so I can find my like terms very easily. It's just a habit I developed early on in my algebra career because I'm not a great mathematician. So what I am is meticulous about my work. So I write multiple variables inside a term always in alphabetical order. Does that mean you have to? No. So to finish expanding this quadratic, we're going to get those three terms. I'm going to distribute the -8, and then I'm going to copy down the +9. Now I'm going to distribute this negative sign, so it's minus x squared plus 8x minus 9. There's the numerator. Now I'm going to look for like terms. There's a positive x squared and a negative x squared. Let's write our next. We're just going to rewrite and clean up that numerator is all we're after. This is the only hx term that we wind up with, so I'm just going to copy it down. This is the only h squared term, so I'm going to copy that down. I have a minus 8x and a plus 8x. This is the only h term. I have minus 8 of them. And I have a positive 9 and a negative 9. Look at that beautiful result. Every single term in the numerator has at least one h in it. And that means I get to factor that h out. And that was what I was after, because that gets rid of my issue with using the substitution theorem. Now I can use the substitution theorem. Now everywhere that there is an h, I can write a 0. I drop my limit notation. Yes, there's a variable there, but it's not the variable that is inside the limit. So f prime of x is 2x minus 8. Just exactly what they said that I was supposed to show was the result, using the definition of the derivative. So there's an example of using the definition of the derivative analytically, and we need to know how to do that. Remember that our process is to try to factor an h out of the numerator that will cancel with the h in the denominator that's giving us mathematical trouble. So we understand and can easily calculate the average speed of a moving car. It's just the slope of the secant line. It's just rise over run. We get the position of our car at two endpoints over some interval that we're interested in. We take those two endpoints, time and position. We find the slope of the line through that. That is the average rate of change of the position of the car. It's given its own name, and that's velocity. But what if we needed to find instantaneous velocity versus average velocity? What if I needed to know exactly the rate of travel at some point interior to those endpoints. I need instantaneous velocity. Well, remember, the derivative is slope of the tangent line. If the tangent line is a line on the position function, then the slope of that line is velocity. And at any one given input value, it's instantaneous velocity. This is the derivative in the context of position. So the derivative in the context of position is instantaneous velocity. Notice there are two forms for the definition of the derivative. Here's the form we've been using. We take the distance, the run, and we take that distance to 0. Here's the rise. This one is a little more intuitive. You probably can clearly see rise over run, y2 minus y1 over x2 minus x1. Notice x is approaching a, and when x gets at a, the denominator equals 0. These are identical. It's just the notation that's different. Why do we use this one as opposed to this one? Because the algebra on this one is easier. Even though you're used to seeing that as speed or velocity in the context of position or changing position, if we take x to a and we use the substitution theorem, meaning we plug a in for x, we're at the same problem we get over here when we take h to 0. But now, instead of factoring just an h out of the numerator so that it will cancel with the one giving us problems in the denominator, now out of that numerator we have to factor a linear factor, x minus a. That algebra is much more complicated than factoring one variable out of multiple terms. So although this one might not be as pretty or as intuitive to you, it's algebraically much, much easier to work with that one. So that's the one we're going to be working with. Know the definition of the derivative. In the context of position and velocity and acceleration, let's look at this graphical example. Graphically, if we're not given a function rule, we can approximate the slope of the tangent line, by using 2 points on the graph and finding the slope of the secant line that has the same estimated slope. These words mean something. This does not say find the bicyclist average speed or find the bicyclist instantaneous speed. It says estimate. So isn't a good approximation for the slope of the tangent line going to be the slope of the secant line? And we'll talk about how we find that and ensure that it is a good approximation. But first of all, let's estimate the average speed over this interval. If they want average, they better give me 2 points. And they do. I start at t equal 1 and stop at t equal 2. So I have 2 points, 1 something and 2 something. Well, I don't have a function rule to plug those t values into. But what I do have is I have a graph that will tell me what the outputs of the function are at those 2 inputs. And I can tell by looking at that graph that when t equals 1, the distance traveled is 15. There's 1 point. When t equals 2, the distance traveled is 20. So the average speed, which is evidenced by the slope of the secant line through those 2 points, it is the difference in the outputs over the difference in the inputs, and that is 5. What are the units? Miles per hour. So the average speed of the bicyclist from t equal 1 to t equal 2, from hour 1 to hour 2, is 5 miles per hour. This has something completely different. What's the instantaneous speed of the cyclist at only that point? What is the slope of the line through that point? Is it going to be the same as the average? We're going to use the average to approximate the slope of the tangent line. But we're going to be careful because we're not going to just use these 2 points. When they give us the whole graph, we're going to go on out here until we can find fairly closely 2 points that we absolutely know we can get the coordinates of. There's 330. And if I was to extend this on out here, I could get the point 0, 10. The slope through this line is going to be a really good approximation for the slope of the tangent line at that one single input value. So we would say the instantaneous speed at t equal 1.5 is approximately the rise over the run. Approximately 20/3 miles per hour. To say that you have 20/3 miles per hour in the context of a speed of a bicyclist may bother you, but don't let it bother you. I don't want to see mixed numerals. Never turn a fraction into a decimal unless you are explicitly told to. Please never, 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 never simplify unless you just absolutely are told to do so. That is a habit I want you to develop immediately. We only simplify on multiple choice tests, and we only simplify when we are told to.